Okay, I think we can resume the session. So next speaker is Luis Cunha, and he will talk about edge tree spanners. So please, Luis, go on.
Okay, thank you very much. Hello, everyone. I'm Luis Felipe, professor at Universidade Federal Fluminense from Brazil. My co-authors are Professors Fernanda Couto and Daniel Posner. Both of them professors at Universidade Federal Rural do Rio de Janeiro. It's a great pleasure to be here talking to you. Also, thank you very much for the program committee to organize the scheduling. Good afternoon to everyone. Actually, here is still during the morning, and it's very nice for me. My talk is about edge tree spanners. So problems with spanning trees are very classical in the literature of graph theory, and it's very easy to solve when you want to find just a spanning tree of a graph, as you may know. However, if we add some constraints on these kinds of spanning trees, such a problem can be much more difficult. And in this work, we deal with a problem that wants to minimize maximum distance between vertices or edge in connected graphs. So this kind of problem is exactly an example of min-max problem, because you want to minimize on the context of maximum distance between vertices here, and what I will define next. So a 3T spanner of a graph is a spanning tree such that the distance between any two adjacent vertices of the graph G is at most T in the spanning tree T. Okay, this T in caps lock here. So we say that if a graph has a 3T spanner, then it is T-admissible graph. Okay, so what you want is to determine the stretch index, which we denote by this parameter here, which is the smallest T for which G is T-admissible. Okay, so the decision version of this problem is we give you a connected graph and an integer T, and you want to know if G is T-admissible. Okay, so if the stretch index is at most this T here in the input, what we give in the input. Okay, so let's see an example to be clear. First here, a cycle graph, a very simple graph here, and we know that any spanning tree of this graph is a path with 6 vertices here, and this is a spanning tree, and any other is exactly like this. So what we should do, we must see pairs of vertices that were adjacent here in the graph that is not any more adjacent here in the spanning tree, and compute the distance. Then for each spanning tree we obtain, we have this parameter, which is the smallest, which is the maximum distance between any pair of vertices adjacent here that is not adjacent here anymore. So here the distance between them is exactly 5, and for any other spanning tree of such a graph, we have the stretch factor, what we say equal to 5. Then we know that the stretch index of such a graph is equal to 5. Okay, because the distance between this pair is exactly equal to 5. Another example is a complete graph, another very easy graph to look for. Here, differently from the previous graph, there are several spanning trees. However, there is a universal vertex here, and then any optimal spanning tree can be like a star, can be a star subgraph. And the distance between any pair of vertices that were adjacent here, now in the tree, is equal to 2. Okay, because there is a universal vertex, then such a vertex is adjacent to any other in this graph. Which implies that the stretch index of complete graphs is equal to 2. Okay, so with these two examples and understand this definition of spanning trees, we define now in this work edge tree spanners. So we add the edge parameter, the edge concept in the graph to obtain such a spanning tree. So we say that edge 3T spanner of a graph is a spanning tree of its line graph of G, such that the distance between any pair of adjacent edge of G is at most t in this spanning tree of each line graph. Okay, so just to recall what a line graph is the intersection graph of the edge of a graph. So very similar to the previous concept, now we are looking for distance between edge in the graph. And we say that if G has such a spanning tree, edge 3t spanned, then the graph G is an edge t admissible graph. Okay. And then what we are looking for is to obtain the edge stretch index of a graph, which is the smallest t for which a graph G is edge t admissible. So if we understand the definition, we see that this problem is equivalent to obtain the stretch index of a line graph of a graph. So determining the edge stretch index of G is exactly the same to determine the stretch index of a line graph of a graph, given as in the input. Okay, so let's see an example to be clear, to understand this. So here is a graph, any graph here, and here we have a line graph of G, and what we are looking for is to minimize the distance between vertices in the line graph, which is equivalent to minimize the distance between edge in the graph here. So in black is the line graph, also here is in black. And just to recall, to review what a line graph is, for any edge we have a vertex, and if two edges share a same endpoint, then such corresponding vertices are adjacent. So AB is adjacent to AC, BC, BA, BD, and here we have a line graph of its graph. And what we are looking for is to determine the stretch index of such line graph here. We can equivalent say that our problem is exactly this one. And as you can see in red, this is a spanning tree, and then the distance between AF and CF is equal to 3, 1, 2, 3, which is equivalent here in the graph G that we can see in this overlapping here. We are overlapping here the graph G and its line graph L of G. So for each edge, we have a vertex here in square, a vertex, and then the edge C, F, and EF are at distance 3 from this path over the edge in the graph G. So with this, we say that G is edge 3 admissible. Okay. How about the literature about these problems? The computational complexity of determining the stretch index of a graph. We know that if I give you a graph and I want to answer if a graph is too admissible, such a problem can be solved in polynomial time. However, if I want to determine if such a graph has stretch index at most t for t at least 4 is NP complete, and still an open problem since 1995. We don't know how to answer this question about the computational complexity of 3 admissible graphs. So if I give you a graph and I want to say if such a graph is 3 admissible or not, it's still an open problem. For long years, we still don't know how to answer this question. And there are several papers dealing with graph classes, approximation algorithms, heuristics, and several kind of stuffs about this problem. But considering this approach, that we can say considering on determining the stretch index of line graphs, there were not any work about that. And hence, what we do here, we prove that edge t admissible is a polynomial time solvable problem for t at most 3. And what you conclude here that 3 admissibility is a polynomial time solvable for line graphs. Okay, so we are not able to solve, not yet. Sorry. the computational complex of admissibility for any arbitrary graph, but for line graphs, we prove that it's a polynomial time solvable problem. Also, we settle sufficient conditions of graphs to be add4 admissible or add5 admissible, which implies that for the graph classes that we prove that they are 4 admissible, we are able to determine exactly this edge stretch index of them, because we are able to determine polynomial time the stretch index for graphs equal to 3, also equal to 2, or equal to 1, as is stated here. And also for some classes which we prove that they are add5 admissible, we are able to characterize sufficient and necessary condition for sure for the graphs that has edge stretch index equal to 3, equal to 4, and or equal to 5, for examples of graph classes. Also, we prove that the edge 8 admissibility problem is NP complete even if the input graph is bipartite. And based on this result, we are able to adapt and to extend this result for any k equal, for any 2k we put in the input here for any k greater than or equal to 5. Okay, so our summary are these results here. So let's first start for this first topic. And firstly, we consider k admissibility, add k admissibility problem for k equal to 1 or equal to 2. So we know by definition that trees are the unique one admissible graphs, because by itself the graph is already a spanning tree. So any pair of vertices that were adjacent before is adjacent here in the spanning tree. So these are the unique cases to be one admissible. Now considering line graphs, we have that line graphs are claw-free. It's a result, a classical result when we are studying line graphs, that they are claw-free. And that claw is depicted here in blue. It's a bipartite K1 tree, complete bipartite. A, B, D, E is a claw. And then such a graph is not a line graph of any other graph, since there is a claw as induced subgraph. So what implies that such a graph cannot be a line graph, but since line graphs are claw-free, and we know that trees are the unique one admissible graphs, we have that path graphs are the unique edge one admissible graphs. Okay, since these are trees that must be one admissible, and for line graphs, only paths can be considered as a tree. Then we have that these are the unique edge one admissible graph. A graph must be a path. Considering trees in general, so if let G be a tree, we have that if G is a path graph, then what we have proved here, this simple observation, is that the edge stretch index of a path is equal to 1. Otherwise, if G is an arbitrary tree, then the edge stretch index is equal to 2. So how can we prove this result? Is just considering any arbitrary tree as the input. So G here is in black, and looking at the line graph, its line graph, we have that for each internal vertex of a tree. So we know that in this example, for instance, B and C are the internal vertex. A, D, E, F are leaves. So for each internal vertex, there is a corresponding complete subgraph in its line graph, of size exactly the degree of the internal vertex associated. So for this vertex B, there is a clique of size 4, because the degree of B is equal to 4, and it's very easy to see that it's a complete subgraph. And also here, the vertex C, which has degree equal to 2, there is a complete subgraph of length 2, so there is a K2 here. And moreover, Any two clicks that are in the line graph, they share at most a vertex. Based on this, we can always obtain for each complete subgraph a spanning star in the line graph. So here in blue is a star considering this first complete subgraph here, and also another star, which is exactly this K2 for this subgraph considering here. Okay, so which implies that the edge stretch index is exactly equal to 2 for arbitrary trees, of course, which are not path graphs. Okay, so now that we know the edge k, determining the edge k admissibly for trees, considering the general graph, if I give you a general graph and if I ask if such a graph is to add 2 admissible, we can also solve it in polynomial time, since the problem of determining the k admissibility for k equal to 2 is also a polynomial time solvable problem. Then just consider the problem for line graph. So if I give you a line graph and if I ask you if this graph, if its line graph has an edge k, an edge 2 admissible, 2, 3 admissible, 2, 3 spanner, then it's exactly to ask if a line graph is 2 admissible, which you already know that is a polynomial time solvable problem. Okay, so now we go for the 3 admissibility, actually add 3 admissibility problem. To prove this result, we must first state this lemma, which says that an edge 3 admissibility is an unitary property for induced subgraphs. What means is that if I give you a graph and such a graph is 3 admissible, so for any induced subgraph of such a graph, this induced subgraph is also 3 admissible. And to prove this, I just give you a sketch of the proof. And my time is passing. I give you just a sketch of the proof. So let us assume first that G is 3 admissible, but it contains an induced subgraph H that is not add 3 admissible. If H is not add 3 admissible, is that H is an add K admissible for K at least 4, okay? Suppose also that G has another subgraph such that H is subgraph of G subgraph of G, which we say G prime. So H is subgraph of G prime, which subgraph of G, and G prime is actually 3 admissible. Add 3 admissible. We know that there is such a graph G prime since G is 3 admissible. So in particular, it could be exactly equal, isomorphic to G prime. Okay. Assume that U is a vertex that belongs to G prime, but does not belong to H. Okay. Since H is edge K admissible, is because there is a path, a K path in H. So let's consider in here, in this figure, a K path for K equal to 5. I think it's 5. Let's count 1, 2, 3, 4, 5 exactly. So there is a 5 path here, and these vertices outside belong to H. Okay. And the U is the vertex that we add to H. And now this graph, this subgraph, is add 3 admissible. So when we add U, such a path, such a 5 path, for instance, here, must be decreased, must be shortened. So there must be something like that or something like that, just to say in a very intuitive way. And for any case we consider here, we cannot decrease it to edge 3 spanner. Okay, so that's why considering here this lemma is true. Why we have this lemma? Because now we can consider in subgraphs that cannot be into a edge tree admissible one. So if you consider a complete graph for k at least 5, we have that the edge stretch index of them is equal to 4. And to prove this result, also just a sketch of that. First, consider K5. K5 is edge for, sorry for that, is an edge for admissible, and we can prove just by case analysis. We can see here in blue and in green are edge of the edge spanning tree. Okay, so here is an example just. But if you see the vertices that are in this green edge, they are at distance 4. And any other kinds of spanning subgraph, spanning tree that you consider here, we are not able to obtain a tree admissible one. So we have also that any kn for any n greater than or equal to 5, this graph is also for admissible. And since edge tree admissibility has an unitary property, then it cannot have kn for any, oops, n is greater than or equal, not at most 5 here, sorry for that, okay. For any n at least 5, cannot have induced in any edge tree spanning graph, admissible graph. Also, another graph classes and another type of graph that cannot be in any tree admissible one are the cycles of length n for n at least 5. Why? Because we can simply analyze that line graphs of cycle are isomorphic to cycle, and cycles of length n are n minus 1 admissible, as we saw in the first example of the presentation. So if n is at least 5, then Cn is not tree admissible, is not edge tree admissible as well. That's why these two subgraphs cannot be induced in any edge tree admissible one. Okay, but how about K4s and C4s? Also, there are examples of C4s and K4s that cannot be induced in any edge tree admissible graph. These are the case. So if you have a C4 that for any vertex inside a C4, the degree of such a vertex is greater than 2, we see that here all of the vertices satisfying this property. It cannot be in any tree admissible graph. Also, if you have a K4 such that any vertex inside a K4, the degree of such a vertex is at least 4. It cannot be in any edge tree spanning graph, as you can see here in red in this simple case analysis here. So what we conclude based on that is that for any x induced in edge tree spanning graph, such that x can be a C4 or K4, we already know that C5, K5, and any other value greater than that, such a subgraph does not belong to a graph. But if there is a C4 or K4, then there must be in C4 at least a vertex of degree equal to 2. And if there is a K4, there is at least a vertex of degree 3 equal to 3. Okay, is another way to state this corollary is saying that. So if you have a graph that has not Kn and also does not have Cn, but it can have C4 and K4, there must be exactly like that. And then what we do, we apply a transformation in such a graph for each induced K4 and each induced C4 that satisfies this corollary, we apply this simple transformation here, that for each C4, we add a new vertex here. So breaking this C4 into a path of length 5, 1, 2, 5, and adding a new vertex here. And for K4, based also on the vertex of degree 3 here in the vertex of degree 2, we break into 3 triangles here like that, and we can prove. Sorry?
Huh?
Sorry?
Sen niye
You want to say something?
başka bir sunum mu? Aynı öndeki sunum mu dinliyorsun? Ciddi olamazsın. Can you get any crazier?
É áudio que ficou aberto, Luiz. Continua.
Nasıl böyle olmuş Monte?
Sorry, switch off your microphone.
Aynı anda seni dinlemeye başladım. Baktım.
Sorry, Luis.
I was mute.
No, because I'm muting everybody.
Ah, okay. So now
Sorry
I think
for
it's
the
okay,
interruption.
no
Okay.
problem.
Go on.
So what we have here, we have a graph that do not have C4s and also do not have K4s based on this construction. And we may prove also that if the previous graph was edge-free admissible, then the obtained graph is also edge-free admissible and vice versa. So if this graph is edge-free admissible, then the graph obtained before, the graph used before for this transformation was also edge-free admissible. Okay. Why we apply this transformation? Because we obtain now a graph classes that satisfy this property here. So a 2-tree is a graph obtained from a K3, and by repeatedly adding vertices in such a way that such added vertex is adjacent to 2 neighbor vertices, which implies in a K3. And a partial 2-tree is any subgraph of a 2-tree graph. What we have that let G be an edge-free admissible. H can be obtained from G from the previous construction. Such a graph is a chordal partial 2-tree graph. Based on the previous result, we obtained necessary and sufficient conditions to have a partial 2-tree graph. And if such a graph is edge-free admissible, then it must be chordal partial 2-tree graph. Sorry for the time, because I don't have time to explain all the details, but we have proved that edge-free admissibility can be solved in polynomial time for partial 2-tree graphs. And then we solve the edge-free admissibility for any kind of graphs. Okay. Now we have proved, as I said before, that some graph classes are edge-free admissible. And since we just proved that edge-free admissibility is polynomial time solvable, then we are able to determine the exact edge stretch index for such graph classes, which already know that are edge-free admissible. We also know when it is edge-free, edge-2, and so on. I think the microphone of someone is turning on. I'll continue. Okay, so examples of graphs that satisfy this property are split graphs, cographs, P4 sparse graphs, P4 tied graphs, join graphs. There are several graph classes that we are able to develop algorithms in order to solve the edge-free admissibility, which are exampled here. Also, we have proved that for the classes for this graph class, which are the graphs that can be partitioned into one independent set and 2 cliques. These graphs are edge-free admissible, and we can characterize it also when the stretch index is equal to 4 and equal to 5. And then based on that, we are able to determine also in polynomial time the edge stretch index for these graphs here. Oops, I think my time is wrong. And then just to conclude 1 minute, since here we are considering the graphs that can be partitioned into independent sets and cliques, how about bipartite graphs? Bipartite graphs, as we already know, are the graph classes that can partition into 0 cliques and 2 independent sets. Here we prove that such a problem, actually, to determine the edge 8 admissibility is NP complete for bipartite graphs. So I don't have time to state the details of this proof, but we use a reduction from 3-stat, and then we have that this graph is edge 8 admissibility if and only if its instance of SAT is yes, is an yes instance here. Okay, so what we are working right now is to develop exactly a relationship between stretch index and the edge stretch index parameters of a graph. So if I give you a graph and I say it's T admissible, what's the value of the edge stretch index of such a graph? We know just for some cases, but not in general. Also, such previous proof, NP completeness proof can be adapted for any 2K problem for k greater than or equal to 5. But how about the odd values of admissibility? We don't know how to solve it so far. Okay, so I'm sorry for the time and thank you very much. And that's it.
Okay, thank you, Luis. There are very short time for questions. Okay,